Okay, thank you to be here. And let me start the lecture of today, opening MATLAB. MATLAB, again, you can send me an email if you want to use MATLAB Simulink. When I speak about MATLAB, I intend also Simulink. Simulink is an application of MATLAB. And I will connect with our IT responsible person, which send us back the information how you can connect in remote, you can use in remote our resource, MATLAB Simulink resource. Basically, when you connect it with our resource, you can see an icon which looks like, I don't know now if I can show you, but it's not relevant. It's written MATLAB. Click twice and MATLAB starts. What is the meaning of start? Let me show you. Once you click twice on an icon in which is written MATLAB, you will see something like, let me show you. But this I already told you, I think, about MATLAB. Something like that. About that, you already know, this frame. I don't want to now to tell you more about this. Today, Simulink. Simulink is an application of MATLAB in the sense is a graphical application. In this sense, it's more friendly. Here, do you remember last time in particular, do you remember when I introduced the PSO? It was heavy, while loop, for loop. Anyway, this really is heavy in the sense of programming. In Simulink, we can use the macros of MATLAB in the sense that we will see some blocks in which inside we have an integral. Inside we have a calculation of minimum, the calculation of maximum. Do you remember in PSO, in the program was relatively difficult to find this maximum if for just to understand what I intend. In Simulink, we can use some macros. Macros are functions in the sense prepared for us to solve some problems or part of the problems. At the very important advantage, this is in a graphical form. Let me open Simulink. To open Simulink, the frame, I would like to say, you can click here twice. Did you see this icon, Simulink? Twice. Or you can write here in the command window, Simulink. Let me click twice here. I share, I hope, no? I share. Excuse me. If you click twice, you can see that you end up in a frame which looks like something like that. Now, also Simulink is really a huge library, it's a huge frame. Let me focalize on some important elements which allows to simulate or to explain how we can build the model of our bank system. And I will use already a prepared file in order to speed up a little bit the lecture, and then we will see more in detail. Today is not possible because we introduced just the Lotka Volterra, but restarting from next week, we will see a little bit more in detail. But let me show. Look here. This, it could be that I can build for you. It is better. It is better. Can build directly without taking an already prepared file. It makes sense. Look here. You can see create a model. We know what the model is. Last time, you remember, I told you at the beginning of the semester, I told you that the model is a way to represent the system. It's not true. We are not looking for the true. It's something which we can use to describe. Create a model means click twice, as always. If you click twice, Simulink try to open an environment which looks like, you remember this environment which we had here, this M environment. Let me show you. in order to understand a little bit the philosophy, yeah, the philosophy. Let me see if I do. Yeah. Now we will see that this environment, which is Simulink tries to open, looks like this M environment. The reason is Simulink is just a graphical interface because Simulink calls, each block of Simulink calls some M function. So a little bit the feeling. Let me consider here, I have my MATLAB comments. And here, and then let me image. So in the upper part, we have some tools which allows to use in a more friendly way what I have here inside. Or yeah, in the lower part, let me say the lower part is nice representation. A low level. I mean, do you remember PSO? Let me see if I have. I don't have here. Anyway, what I am here in this M file, think about the PSO program, is we say in informatic language, is low level. I mean, you have to put semicolon, you have to put C equal something, you have to put 4. We are at low level. Now, at more high level, we have some blocks, which these blocks do that for us. Of course, we have to know what the blocks do in this sense. Let me going again in Simulink environment, not only environment. Now I am exactly in this create a model. I am in Simulink, but I am in an interface in which I can create a model. Okay, let me see if I have now here the model of the bank which we have seen last time. Otherwise, I open the lecture. I will open the lecture because probably it's something faster than to look here. Okay, it doesn't matter. Let me open the lecture and then I will translate the information which we had in the lecture, the mathematical model, into Simulink in order to show you what happens in the liability if I put money in the bank. This is a little bit the idea. To look, does my liability, or the liability, even though it's not my liability, it's my money, which is the liability in the context of the bank, which is, I hope that going up, otherwise I don't need to put the money in the bank. I would like to show you this example, directly building here without taking the already prepared software file, because it seems to me a little bit more constructive to show you. Okay, let me open the lecture of last time on a couple of slides. Yeah. I received also a question concerning the examination. Did you receive the email with the information about the projects? Yeah. Even though we discussed a lot, but probably last week or before last week, we had some problem in my study because I have the feeling that they already sent, but you remember we had some problem. Anyway, some student asked me if it is possible to upload before. Before is always possible, before at the end of September, something like that. It could be possible so later, as I told you, but this I will confirm in the middle of September or so early. This is also valid for everybody, as I told you last time. If you already upload it, and if I say, please pay attention, we have 2 weeks more, you can re-upload, no problems. Because if we have a prolongation, if we can postpone, this is valid for every student, not only. Sometimes it happens, as I told you last time, because I don't. We have also this semester a student who is working in my lab, combining the bachelor and this complementary course. This means sometimes we need time for the experimental setup. It's not only MATLAB, but we have some hardware systems and so on. Okay. Now, do you remember the name? That was the problem here. provided input here. Um, huh. Was lecture number, if you, oh, okay, in my, is there in my study? Yeah? One second, probably I'm able to find. Let me see.
Lecture 4 is on my study.
Exactly. Let me see if I found now quickly. No. Uh, okay, okay. Probably I found. I didn't have time to correct this. Do you remember there was a sign minus plus, but I told you what the error is. At the end, the result were correct. Okay, was correct. Let me share. Ah, this block. Okay, okay. I think you. Oh no, it's impossible to work. Ah, I think you should see the presentation. I hope because with this Zoom is always a problem too. Excuse me, I lost now. I don't know what you see. Okay, I hope that you see the lecture. I hope that I am not able to. Do you see the lecture here on the computer? Because today is also a problem to understand where I am. I hope that you can see the lecture, but I'm not sure. Yeah, I think so. Now, the idea is, let me show you how we can build. Uh, let me start with this. This is a little bit too complex. Let me start with this. The liability model or dynamics, the dynamics of the liability in continuous. As I told you, this is not a realistic model because the bank is not a continuous system. I clarify this. No, the contract in the contract is not written that you receive the interest each micro nano picoseconds. Each day, not necessarily each 3 months. This means TS, the sample time, we will see, is not. I mean, the sample time is something which must be defined in if you want to simulate in the real form, in the form which reflects the reality. Let me nevertheless, in order to introduce Simulink, to simulate this system here, which nevertheless represent the liability without assets, as if the bank works just with the liability, which we have an input. I put money, I withdraw money. We have the dynamics of the liability, which is connected with the beta multiply IL, which is our netto interest. very, very quickly explain. This means, look at this equation here. Please keep in mind, we will come back. And let me show you how we can build this equation, including its initial condition. You remember, L at time 0 equal $1. The idea is, I put $1 in my bank. I sign, let me say, my contract with an interest netto, I don't know, 3%, 5%, it doesn't matter what. I hope that I will be able to see that independently let me say I don't do anything, no, I don't invest any money. I hope that nevertheless, in accordance with this netto interest, my liability, my money, will increase. Probably I would like to ask another thing. I asked last time, are you able to calculate, put this equal 0, are you able to calculate the solution of this differential equation? The derivative of L with respect to the time equals the coefficients, a coefficient which is beta multiplied IL multiply the liability. Are you able to figure out which kind of solution we have? Not a solution of the differential equation is known, is not known. I give you a differential equation, this one. I put U equals 0. I put L of 0, the liability, that means the money which is in the bank at time 0 when I start to simulate, when I start to observe what happens, equal $1. If I say, are you able to calculate mathematically what happens in the system? Say no. If it's not able, we are not able to do. Probably I show what I intended. Yeah, and then we simulate. It's better to do that. 1 second, I take something to write. Second. It's too difficult, my language, a little bit. And that doesn't matter. Now we will simplify. Okay, look. Oh. Today until 8 o'clock, no? Definitely. Quarter past, yeah? Quarter past, okay. No, do you have a bus? Okay, 8 o'clock is okay. Give me half hour, excuse me. But again, today I have a good motivation too. It could be also next Monday, but I hope no. I hope to be in a better shape. Why? Okay, now here. Why I don't see the lateral camera? Okay. Look, as I repeated, I have this differential equation. This we considered in the last two lectures this year. No, we talk a lot about that. Beta multiply IL isn't a parameter. Do you remember in order to distinguish netto gross the coefficient, which represent, let me say, beta multiply IL, the netto interest which I receive. Because I put the money, I trust the bank, I put the money which belongs to me in the bank. Let me consider just this one without U of t. U of t is what I put in the bank or what I withdraw. Could be positive if I put money, could be negative if I withdraw. Let me consider just this equation, this model, considering nevertheless an initial dollars, euros, I don't know, dollars. Question, did you see this differential equation in mathematics 1? Yeah. The engineers, of course. The differential equation is basically the same in an RC circuit, in an RL circuit. Therefore, our fields system theory is extremely powerful because when we have in the frame, when we know a little bit something about modeling, when we are able to use some tools as Simulink, but not limited to Simulink, MATLAB, of course. When I speak about Simulink or MATLAB, I intended both with one word. It doesn't matter which word I use. Believe me, you can use this knowledge modeling biological system, economical systems, electrical system. This equation here can represent exactly also the dynamics of an like a motor. It's not exactly, but an RL circuit or RC circuit. L is the inductance of a coil. C is the capacitance of a capacitor. Anyway, let me remain on our system. Look, I can demonstrate, but I don't have time, that L of t is $1, which multiply exponential function of beta multiply IL multiply t. In which this is the initial condition. And this expression here satisfies this expression here. Satisfies means is the solution. What is the meaning of this word? Is in mathematics, is something, how possible to say, can scale as find the solution of a differential equation. We are not here for the differential equation. I have a course in master dedicated to differential equations. Here is a little bit to understand the meaning of what we are doing, and in particular to be able to simulate without knowledge about the solution of the differential equations. Nevertheless, if I try to plug in this expression here, we will see that I will satisfy this condition. This means this left part will be equal to this L right part if L equal this one. Including this condition. Of course, look, you remember in high school, this symbol here means that both conditions must be satisfied. Do you remember in high school? Now, we don't need to do the different. I have a course, also in bachelor. The name is Dynamical Systems. If you like to go in depth on differential equations, you can select this course as a selected course, something like that, or elective course for your career. The name is Dynamical Systems. I do differential equations. Then I have another course in master, a little bit more advanced, in differential equations. The differential equations represent the models. Look, why this function satisfies this differential equation, which is our model, and represent the dynamics of the liability over time. Because starting at time 0 with $1, we will see my liability, let me say my capital, we will increase exponentially. Look, why this is exactly the solution of this differential equation. This means L of t, which satisfies this equation here. Because if I plug in here, the derivative of this is, I don't know if you remember in high school, the derivative of this exponential function. The derivative of the exponential function, it itself. You remember this? You don't remember, it doesn't matter. Now, if I put this directly, it's a trivial condition, which is left equal right. This means this expression here satisfies this equation here. The equation means that the left part is equal to the right. I found something, an entity, a mathematical expression over time, today, tomorrow, t is the time, which satisfies this model here. Is this satisfied? Of course, because if I put here 0, exponential up to 0, remember, is 1. 1 multiply 1, this is 0, because I am trying to verify what happened at 0. We have $1, which is exactly what we have here, roughly speaking. Let me now simulate, because we are not interested here to solve the differential equation, but we are interested to simulate. Look, yeah. Look how I can simulate the differential equation. If I go here in the library, here inside, you can find a very huge library, and you can see many, many options. One of the most important is this one, of course, commonly used blocks. Of course, it's most commonly used block. Here inside, we have many blocks. As you remember, I told you that you have blocks, macros, you can call in different form. Yeah, here, for instance, you can see that you have an integrator. Why integrator is for us important? Because the integrator is the inverse of the derivative. You remember in high school. Click on the left with the mouse and drag in our simulating environment. Now at home it is possible to see, but now I hope it works. No? I switch with the lateral camera, I will show you. Basically, clicking on the icon, on the block, maintaining, clicking, and then drag, move, maintaining, and then you can put here. Look. Why this is important in our context? Even though in the equation I don't have an integral, but I indirectly have an integral. You remember in high school, integral derivative, they are close. Colloquially, they say. Here, I can write, for instance, if I click once on this environment, appear this window, let me say window, it isn't a window, no? In which it is written create a notation, which represent, I don't know if you remember in our PSO software, represent the comments. Remember, after this percentage, I can write anything. Paolo is stupid, something like that is in a comment, impossible. And then create a comment, suck. If this is the reliability, which I want to, let me say, simulate, which I want to control eventually at the end, here we have the derivative. I don't know if you remember, because the integral of the derivative is exactly the function, including the initial condition. Or minus, to be precise, the initial condition. Let me write here. I don't know if you agree with this. And the initial condition here inside, if you look here inside, let me look together with me. Here inside, you can put my $1. This means in output of this integral, I will have $1 plus L of t, starting from $1 plus what happens for L of t. I don't know if you remember this a little bit. Let me see if I can explain a little bit better. But I think we come back a little bit late. I think it's understandable what I told you. Now, look at this equation here. Exactly what we can see here. we have this and this already represented. Now I have to consider this. And a coefficient, beta multiply IL, multiply L. This means the derivative, which is here, is equal a coefficient, beta multiply IL, multiply L of t. Let me build this. I go again in common use block. Quickly, I will put here, I click and block again, which represent a possible product between with control R, I can reverse control R twice, I can reverse again. I can now, excuse me, connect this block here with this block here. In this case, I have what I have here. Thus here, I have thus the derivative of L of t with respect to t equals 1 multiply L of t. I don't know if this language could be understandable. Think a little bit. This block means that this signal, this variable L of t is multiplied by 1. I can write whatever I want. This is our beta multiply IL, for instance. A little bit high. Let me see, let me consider something realistic. If I go here inside, let me show. Let me consider an interest 5%, something like that, per year. Even though here, I didn't tell you about here is the time to abstract. In fact, I told you it's not so really appropriate to speak about a bank considering a continuous time. We will see also today the discretization of this. Let me nevertheless simulate this. I don't know if it's clear. This is quite abstract. The integral, this is an integral, this is written, of the derivative of something, considering the initial condition, equals the initial condition $1 and L of plus, let me say, L of t. Let me write a little bit better. But the derivative of L of t with respect to the time, in accordance with the model which I introduced mathematically, equals what in our specific case? L of t, this block here realizes the multiplication of this coefficient and this signal here. This means here we have exactly my beta multiply IL, which is in our case 0.05, for instance, multiply L of t. This loop represents the dynamics of L of t. There is a loop because on the left we have the derivative, and on the right we have something which is the derivative of L of t. On the right we have L of t somehow. Let me try to simulate. Probably we can improve also the explanation later. Let me try to simulate. To simulate, we need just a scope, which you can find, I think, again in common use block, I hope. It's not. This means the scope is in things. Let me see. Yeah, we can see in instrumentation. We have many elements to represent the signal. I don't have time really. Yeah, we need a course to explain all options which we have. But here is one of the most important also for the project, because you can copy the picture and you can the figures and then I show you, and then you can import directly with copy and paste in your report. Anyway, again, click on the left, maintain clicking and drag here. in the Simulink environment. What we want to see, this here. Let me run the simulation. 10 is the stop time if the interest is calculated per year. This means 10 years. You can give any meaning, it depends on the unit which we are using. If the interest is per year, 10 is 10 years. If the interest is per month, 10 is 10 months. No fixed meaning. You give the meaning in accordance with respect with the data. I don't know if this is clear. Question me. Yeah, you can so interpret. You can interpret also so. It's not exactly in mathematicians could give us, but you can interpret it. Yeah, of course. It's an impossible way to understand. You can, let me say, you can figure out. So, yeah, you can figure out. Yes, it's not wrong. It's not wrong. Let me. You don't have UT, no deposit, no withdraw. This is the meaning of the dynamics. It's exactly the difference between liability and general money. Because in my wallet, I don't have liability. I have just money. I'm not expert, but we received, I told you, an award with the student of this course some years ago. I didn't show you, no? Not yet. The certification. The student of this course. Inside a bachelor thesis, after the course, he wanted to invest its time and go ahead in this direction. And we received the best award, the best paper award in the conference in control. But we implemented, a little bit advanced algorithm, Kalman filter, MPC, model predicted control, model to predict to attain, I don't know, in 2 years, $1 million in back. This is what the idea. Look, as I told you, we have started from 1. Now we cannot really recognize this exponential function. But believe me, if I simulate more than 10 here, you can realize this, that I will have an exponential function. But in any case, the idea was should increase and not decrease, otherwise that's not worthwhile probably to put in the bank. Okay, now I show you what happens in the loop if I put the U, and then I will show you the discretization, then we will start today with the LOTCA-Volterra, and then we will go ahead on this Simulink MATLAB with the LOTCA-Volterra control. But in order to control, we need an input. Clear? Here, let me come back, because in the course, in the title is written also control, extremely important. For everybody to be able a little bit to control our life, to control our money. In order to do that, we need an input, something in which I can do in the system. Here, I cannot do anything. I mean, it seems to be that I receive an heritage. They put $1 in the bank, and then everything is in the hand of the bank. I cannot also withdraw money because I don't have no variable which represent this action. Very important. This is in a language a little bit new for you, but it's interesting, I hope. Now, how I can put my which gives me the possibility to change my life, my money and the bank. Increasing deposit plus decrease withdraw. So I can use this heritage. But the concept of the dynamics is important here, this loop, which in my wallet remain constant. If you consider the inflation, here is not increased, not included. The system is a little bit more complicated, but in my wallet, it's going Now, here it depends on the interest. Anyway, it's complex. I didn't tell you about how the inflection change the loop. It's just a little bit more complicated, but this could be a possible project if you want. We did already with some students. Basically, starting from some simulations, which I don't have time to tell you, we can go ahead with including the inflection in this dynamics. Here is no inflection. Of course, the inflection change a little bit the curves, reduce but the inflection is an extremely complex concept. And not expert, but we have a model in the literature. We can consider this. More important for us is you, because we will see in the LOTCA Volterra, we receive the award with a student. This I told you, with this Fisher dynamics. I didn't tell you. At the end of today, 3 minutes, I will show you. Because help to motivate you a little bit, no? Because it seems to be everything complicated, but I hope that I at least was able to give you the feeling that we can do something. Look, with input. You remember in the slide, plus u of t. This means the change. What is the meaning, the practical meaning? What change in my liability? Do you remember the derivatives represent the changes? The changes is a function of the capital multiplied by the interest plus what I do. I can put money inside or I can withdraw. We will see better now in a few minutes in the discrete form, because I would like to show you the discrete form, because last time we dedicated a lot of time on the discrete form. But here, conceptually, it's okay. No, I mean, the changes, how I can change my liability, my money, let me say, roughly speaking, my money in the bank. Of course, something depends on the structure of my contract, of course, on my money, in particular, my initial value, and plus what I do. It seems to be intuitive. Now, let me introduce this element here and the loop. The initial condition remain the same. Here I didn't put, but remain the same. At time 0, I have this heritage, no? $1. Look at this element. It's extremely easy to include here, because now the derivative is not only this plus u of t. This means if I go here on the library, again, as before, let me share. If you go to the commonly used blocks, I hope, the most important, one of the most important, look, here I have this sum. Click on the left, maintaining, and drag. This means now the derivative, let me switch with the lateral camera. The derivative of the liability over time is equal this as before plus u of t, which typically, why does it work? Okay, which typically came from a controller. Now we will see in another context what a controller is. The controller is our algorithm, which we have in build. We can do this for the project in our computer. We will see in the context of a LOTCA Volterra, but the controller does not change much, because the controller at the goal intend here to obtain 1,000 euros in my bank, or dollars, and in accordance with expenses, in accordance with what we want to buy, try to offer you a plan of investment per year in order to obtain, I don't know, 1 year, 2 years, doesn't matter what you desire. This is an algorithm. We received this award, this paper, using model predictive control. This means based on the model, we do some predictions, and then we say, to this year you have to invest this year you have to invest another amount, you have at disposition this amount to go out to buy, I don't know what. But at the end of my prediction horizon, my desired horizon, we will receive back, I don't know, 1 million euros. This is the control. The control is an algorithm. We generate U of t based on L of t, on A of the assets. The system is quite complex. Let me put here an input now. Let me say that each year, if our unit is here, I put $1. We can see now the simulation, what the change in the output. How I can do that? I go again in these convolute blocks. You can see constant, exactly 1, but I can change 10, I can change whatever I want. Let me share again. Now we can see that the changes of my liability depends as before on the interest multiplied the capital, but also what I'm doing could be also minus, but could be also in a function, a complex function, the input, which came from a complex algorithm. We consider L of t, assets, inflation, which is not there because really this is complex, extremely complex. But you can think that we can build and will be able at the end of the project. Believe me, if you want to apply, if you want to go ahead with this field, it doesn't matter which field. The controller can control every kind of system. Again, you can realize also that the models with this tool, let me say, the models are more or less the same circuits. I will increase also this feeling. Let me show you the simulation now, and let me do a discretization. We will see that will not change much. We increase nevertheless our money. Of course, we have to compare with the other one in order to see the differences. Here at this moment, we cannot see really basically the difference, but it could be, if you remember, take in mind, consider this, keep in mind this value, yeah, a little bit more than 14, right? Yeah, at the end of 10 here is a little bit more than 14, right? What is written here? 14. Now, let me look what happens, what happened before. Excuse me. Should be visible. If I disconnect here and we don't see many difference, right? This is really almost the same. No, it's strange. It seems to be that is larger than before. That cannot be, right? It was before, no, 1,6. Okay, makes sense. Before was 14, right? Because from here I don't see. Now is 1,6. We can see, it doesn't make sense. No, it's okay. This is without input, no? Yeah, that makes sense. And look, if I put minus, please, I don't share, but believe me, at home, if I put minus 1, this means I will withdraw each year 1. At home, you didn't see what I wrote, but I changed the input in -1. Look, Of course, I started with $1, and of course, if I receive 3% each year, and each year I withdraw €1, you can believe that this is credible solution in the sense of differential equation. Is the profile of my account in the bank. Let me do the discretization of this equation here, because nevertheless can be used, because I have to consider just what happens here at the first year, the second year. In the middle will be constant, because in the contract you don't receive interest until the end of the year, or until the end of the contract, depends. And what I put and what I withdraw is calculated at the end also. But of course, here it's a little bit strange, because continuous is not exactly what I observe in my account. Now, let me see exactly what I can observe with my account. Let me come back on the lecture. Yeah. You remember I told you a lot about this equation here. Assuming TS 1 year, 1 month, it doesn't matter what. We have to know, assuming that this interest is calculated 1 year, 1 month, is written in the contract. This was the related discretization of the discrete liability dynamics. Try to do at home eventually the rest, assets, combine both. But anyway, I have already prepared files if you want to go ahead with the project. But let me simulate this for you. This is exactly what we have in a real bank if I consider just the liability. Look, I have to now to build the dynamics and discrete dynamics with reflex related to this equation here. This means L of k equals L of k minus 1 plus Ts multiply beta multiply IL multiply L of k minus 1 plus Ts multiply U of k minus 1. Let me show. I will simulate here. Okay. If here I have L of k, at this moment it's quite abstract. What is the meaning of this? The meaning is we have, again here in the library, I think this we can find in the discrete. You can see that we have a block dedicated to discrete, because in particular, here in discrete, we can see that we have unit delay. What is the unit delay? Let me click and drag. Let me show you what I did. Let me control EI invert. Look. If this is L of k, this block here realizes a delay of L of k of 1 step. 1 step means 1 TS. This means here inside, I will write that the delay equals 1 TS. I go here inside. Let me share. Where is now to share? Yeah. Let me write TS. Excuse me, the initial condition is $1, right? Sample TS, we will define later in an M file or in the command window. It doesn't matter what is, could be 1 month, could be 1 year, could be 1 second, typically, I don't know, in the back 1 per year. But not necessarily, depends which kind of investment. I'm not expert. Now, if you agree, what happens now? Does this block, now it's red because I didn't define TS. that this block realize LK, the relation between LK and LK minus 1. Look, L of K is known somehow from the model. Look, because L of K is L of K minus 1 plus Ts multiply beta IL L of K minus 1 again plus Ts multiply U of K minus 1. Now, let me realize the sum of these three elements. Keep in mind, a few minutes I'm ready. No? And next week we will start with the block Lotka-Volterra. This means I need in the block, let me copy from here, Control C, Control V. I need three elements, you remember? This means I can click here inside, I can choose a rectangular form, and I can add the plus. Then I have U of t multiply ts. U of t was this. You remember? I will define ts later. Again, let me show you again what I intend. I have to realize this. It is written here that my model is L of K equals this three element. I already put this. Now, here is easy. And this also is not difficult because it's enough to multiply the same L of K minus 1, but Ts multiply this. Let me show. Really a few minutes, and then next week we will start. Yeah, we have something like that directly. To remember this. We have three elements. Ts multiply U of K minus 1. We have L of K minus 1. And here we have L of K minus 1 multiply Ts multiply 0,05 because it's written Ts multiply, I made a mistake with 0. Yeah, excuse me. I put O instead of 0, I think. Right, now. Yeah, I don't know if you agree with this. This must be again multiplied by L of K minus 1. Now we define Ts in M file, or do you remember the use of M file? We used the, I think once at the beginning of the semester is the data file. Here should be done a little bit easier. I am ready now. 1 second again. Where is MATLAB? I have to define, for instance, here, I don't know, Ts equal 1. You like? If everything is based on year, it's year. If the interest was calculated and was fixed by the contract per year. Let me now simulate, and then we will conclude. Let me put here both solutions. How we can do? I can go again in the library. What is the library now here? This. Okay, I think this block which I need can be found under, I don't remember, senior routing, I think. Yeah, under senior routing, you can see here max. Click twice, click maintain and drag. What is this max? this max realize a vector of, in this case, 2 signals, but could be n signals. Basically, here in the output, we have the first signal and here the second one. In order to compare both dynamics, the continuous dynamics and the discretized one. Let me now look. Matra will be simulating, no, Matra is the same. We will use 2 different colors. Now the example was with -$1. But look, exactly what I told you. I mean, really, we have the blue line. I mean, if the contract is written that the capital, the ability, the money, let me say, will be updated at the end of the year or at the end of the contract, we can see that what happens in between, you don't realize. We can see exactly from here that we start with $1, but you draw $1. Then remain at 0 here. Then, of course, we have the interest, but we can see a little bit that is not exactly -1, because -1 means without interest. Let me see. Why that? Why this value? Because we have an interest of which we receive, but of course you withdraw more than the interest. Try to do at home. Now we'll upload my study, but we can do +1. But we can understand should be, I don't know, better or not better. But anyway, minus is something which is not basically not a good situation, because we should simulate here the passive interest that typically is not equals the active interest. It could be also another interesting project. I mean, here we have an interest fixed for active and passive, but it's not. If you go with minus, they apply a different percentile, I think. I don't know. It depends if you have some particular agreement, but otherwise we have a penalty. I don't know if directly, probably there is a threshold, understand what I mean? If you go down, go under 0, 1 cent, probably nothing happens, but I'm not sure. Anyway, I hope that I try to show you how interesting, how you can really realize something practical. Starting from next week, we will see something more complicated. Logica Volterra is non-linear system, and then I will have the possibility to simulate also controller. The controller or controllers, we will see one controller, because I don't have time. But for the project, we can apply any kind of controllers. A controller is a function of the error, a function which depends on the state of the system, the states of the system. I already told you about the states, which generate an input for my system. It doesn't matter if the system is Fisher, it doesn't matter if the system is reliability assets, it doesn't matter if current voltage. Believe me, this tool, this mathematical tools connecting with this software, it doesn't matter if Python or MATLAB, allows really to be applied in any kind of dynamical systems. Okay, I will stop here. If you remain, I show you a little bit to motivate you, Scopal award exactly from this course, but it's not mandatory to remain. Let me stop here. I am here for questions. Oh, I stopped recording, but I am here. No? Thank you. No? I hope that it was not boring this time. I am here for questions. Let me see how I can stop. Yeah.